Okay, welcome to the third part of your KIN 225 lecture for February 24th. In this third part, I want to cover neural anatomy and I'll see if we can get into the different types of movements as well. So the basic makeup of the nervous system is you have the central nervous system and the peripheral nervous system. I've left the top blank because I think you know what that should be. It's the brain and the spinal cord, whereas the peripheral nervous system are the nerves extending from the brain or spinal cord and sensory receptors extending from the periphery to the spinal cord and brain. So an example of those sensory receptors that we've covered before in the muscle, that would include your Golgi tendon organ and your muscle spindle. Now I've got an exercise that I set up on the PowerPoint, and it's to use the descriptors of the different parts of the nervous system to fill in the boxes on the neural anatomy slide. So here I have some blank boxes. You have the central nervous system here. You've got the peripheral nervous system down here. You can see there's interactions between all these boxes, and this is what you have to fill in on the boxes. So the top part is the cerebellum that is involved in coordination of movements, fine-tuning of movements. It receives information from spinal reflexes and sends information to the brain stem and the cerebral cortex. The cerebral cortex is just the part of your brain that's involved in planning and initiation of movements. Then your sensory receptors, you're familiar with some of these, the Golgi tendon organ, the muscle spindle. There's other ones, including joint proprioceptors that allow you to sense the position of your limbs. There's receptors in your eyes, in your ears. You have your muscle, you have your spinal cord, and then you have your brain stem. Your brain stem is involved in posture and hand-eye movements, allows one to focus on sensory inputs. It receives information from the cerebellum and also visual and vestibular inner ear receptors and the spinal cord. The vestibular receptors are involved in control of balance. And then the brainstem sends output to the spinal cord. So if you take all those descriptors and try to put them in these boxes, this is what you should get. You should get the cerebral cortex or the motor cortex at top. That's in your brain. You get your brain stem kind of at the base of your brain. Same with the cerebellum. And then you get your spinal cord. And then down here you have your muscle and your receptors. The next part I want to get into here is the control of movements. So there's three different types of movements. There's voluntary movements, reflexes, and rhythmic movements. We've kind of already covered voluntary movements and reflexes, but I'll go over them briefly here. A voluntary movement requires integration of the cerebral cortex. In other words, it just requires activation of your brain. Your brain then sends messages down to your spinal cord, to your motor neurons, and then that activates your muscles. So that's voluntary movements. It's all initiated at the brain. Reflexive movements can be reflexes coming from sensory input, so vision or vestibular, so that's from the inner ear to control your balance, or it can come from muscle. So muscle, we've gone over examples, including the muscle spindle or the stretch reflex and the Golgi tendon organ. It can be modulated by higher brain centers. So recall that I mentioned that you could override something like the inhibitory effect of the Golgi tendon organ on muscle contraction. And these reflexes are involved in posture. Rhythmic movements are kind of halfway between voluntary and reflexive. They're initiated by the cerebral cortex, but they're sustained without input from the higher brain centers. An example would be walking. So for example, walking to walk across a room, you first have to think about it, so you have to initiate it from your brain or your cerebral cortex. But once you get walking, you don't really have to think about every single step. So it's more almost like a reflexive, but it's called a rhythmic movement. So it involves initiation with the brain, but then once you get it going, you don't have to think about it, or you don't have to use your brain to keep it going. Again, an example would be walking. So some questions here: can walking be reflexive? So can we train someone that's lost the ability to walk to learn how to walk again by using their reflexes? And can you do that without really that much input from the brain? So this has implications for someone that's had, say, a spinal cord injury and they've got paralysis or partial paralysis of their lower limbs. You have a part of your spinal cord that's called the central pattern generator. It's a network of neurons in the spinal cord that control locomotion. So this is the part of the spinal cord that is targeted if you want to do rehabilitation on someone that's lost the ability to walk. So, for example, someone with a spinal cord injury or paralysis of the lower limbs. Now, the central pattern generator, it doesn't require input from higher brain centers or reflexes, but it can be modified by input from brain and reflexes. So if you've lost your ability to walk and you can no longer send messages from your brain to your motor neurons or your central pattern generator in the spinal cord because you've had a spinal cord injury, you might still be able to use some of your reflexes to train to activate the central pattern generator to help someone in rehabilitation to learn how to walk again. So I'm going to go over some examples through some videos of people being put through rehabilitation exercises using this concept. But I'll go over some diagrams first, showing you how the central pattern generator is associated with walking and also reflexes and the brain. So here you have the central pattern generator. Again, it's part of your spinal cord. It's a set of neurons in the lower part of your spinal cord. It controls walking, and if you can activate that central pattern generator, you can turn on the walking muscles and get that rhythmic movement. So it can be controlled without control from the brain or reflexes. But the key here is that it can be modulated by the brain. So the brain in a normal state would activate the central pattern generator. But in a rehabilitation state where you have a severing of the spinal cord or partial paralysis with a spinal cord injury, and you no longer can transmit that information from the brain to the spinal cord, you might be able to use reflexive feedback or sensory feedback to control that central pattern generator and help to reestablish these neural networks to help someone to learn how to walk again. So what I have for you here is a couple of videos. I'm just going to quickly pull them up on my other computer of someone being put through these rehabilitation processes. So this will just take a second here. So here's the first video I wanted to show you, and this is kind of the old-fashioned technique of a couple of physical therapists helping this person, to use the sensory reflexes that they get from the feeling of their feet pounding against the treadmill. That theoretically could help to reinforce the neural connections to the central pattern generator and hopefully over time help this person to learn how to walk again. So they're really pounding his feet there, so he gets a good feeling of the treadmill against the feet, and hopefully that activates the sensory receptors in his lower limbs to help with that central pattern generator feedback to help him to regain control of his lower limbs in that walking fashion. So that's kind of the old-fashioned rehabilitation technique. Now they've got some newer technology. So in this case, it's the same concept. Someone that has a brain injury or a spinal cord injury, and they're learning how to walk again. In this case, they're using a robotic system to help move their legs on the treadmill. So it's more of a controlled pattern here. So you can see it's a robotic system that's doing the same thing. It's initially controlling his legs so that he gets sensory feedback in his legs, feeding back to that central pattern generator to help him reinforce those neural networks to help him to walk again. And with this technique, what they would do is they would slowly take away the assistance of the robot over a number of training sessions as the person regains control of their legs in a voluntary fashion. So the last thing I have for you here is just a neural study that was done with this this type of rehabilitation techniques. This is the effects of 9 weeks of locomotor training, as you saw in those videos, in someone with an incomplete spinal cord injury and on the motor unit recruitment pattern of the quadriceps. So this is healthy individuals. Typically in a healthy individual, they can recruit about somewhere around 95% of their motor units voluntarily. You can see the person with the spinal cord injury, before training, they were quite weak and they could only recruit maybe about 35% of their motor units. After 9 weeks of that type of forced treadmill training, you can see they had a significant increase, almost 60% of their motor units they were able to recruit after that 9 weeks of training. So they actually saw an enhancement in their ability to recruit motor units with this type of training.